There we go. Yeah. Yes.
So when you're looking at, I'm looking at liquid solid phase diagrams, and there's like a question on the quiz that I got right just because I guessed the second.
Yeah.
But whenever you're talking about like what's left in the pot, which part of the graph is that like correspond to? After you boil it off, is that what's left in the pot, or is that what goes over to like?
Okay.
You know,
Let's see. Is that one of the ones on the homework? This one here.
Yeah.
Okay. So this one is a. Let me clarify. You said liquid solid, but let me.
I was looking at the example that you told us, but yeah, it's also on the quiz.
Yeah. Okay, so looking at this one on the quiz, this is a partially miscible liquid system. So down here at the bottom, it's all still liquid down here. It just has separated into two liquid phases. Okay, then up here, because you have the black line on bottom and the blue line on top, the black line is the boiling point curve. So that's the boiling point and composition of the liquid, and then the blue is the composition of the vapor. Okay, and what we would call the condensation line. So if you have gas and you cool it down, it starts to condense. The liquid that condenses is over here. You should draw a horizontal line. So let me. I saw confused looks on that. So let's go above B here. I start to cool it down. Right now I've got about, what would you say, 80% B, 20% A. I come down here and I get my first drop condensing on the side of the flask or whatever it is I'm cooling. That vapor creates a drop, and the composition of that drop is right here. Okay, so you start to cool it down, and that drop condensation is right here. So if I were to pull that drop aside, that's how concentrated in B it would be. Because we're already below the boiling point of B. We haven't gotten below the boiling point of A, so there's not very much A in that at all. It's mostly B, because B is such a high boiler. We cool it down to here, we start to see. Now, if I get here in the middle, like where my little cursor is, can you see that? Then on a mole basis, we would do that lever rule. My overall composition is 80% B and 20% A. If I stop right there at that temperature, then the drops, there's like half the moles are in the liquid phase and half the moles are in the vapor phase. Because I'm right there, you draw that horizontal line, and where I'm at with my cursor is the fulcrum, and you have the lever rule, and you have half the moles as liquid and half the moles as vapor. And you've got the composition of the liquid phase and the composition of the vapor phase where the blue and black line are. Now, if it's in a sealed container and I keep cooling it down, eventually I get down to here where the vapor phase is almost all gone and it's almost all liquid. And if I keep cooling and I get below here, then I'm all liquid phase, and it's 80-20, 80% B, 20% A. In between here is when you have two different layers, two different phases, and they have different compositions. So in that two-phase region, you have different compositions depending upon where your temperature is. Now, what we don't show on here is volume, and volume would be adjusting too. So this might be one of those piston situations where I'm cooling it down and the gas is cooling, and so the piston, the volume is shrinking and shrinking. And so we just don't show the volume on here. We can think about what's happening to the volume. Here we still have mostly gas, so it'd be a big volume. Here we're all the way shrunk down to only liquid, and so we'd have a small volume. And then, yeah, so.
So if we were, like, in this instances, if we fractionally distill A, like what would still be in the bottom of the pot?
Okay, so fractionally distill A. So if we keep distilling A, we come up here and we do this zigzag down here. This would be in the collection flask, right? And A, let's see, it would boil, and we would be losing this little point here. I said A, but I'm going to talk about this little lowercase a. We boil that. It comes up here. This is the boiling point. It's a homogeneous solution here, and we would be pulling off the azeotrope in the collection flask, right? And so then the pot would creep uphill. And so in all these fractional distillations, the pots creep uphill. They go towards the higher boiling point on each side, whichever side they're on. And so I'd end up with dirty B. So in the pot, I end up with B, but I also have the non-volatile residues. I have all the other junk. Like some of these molecules will decompose. They'll be real close to the heating element. They'll get super hot and break apart and oxidize if they've got oxygen in there. So a lot of those things just contaminate your pot. And so you never get pure B out of the pot. You'll get dirty B in the pot. Now, if you reach this point, if the azeotrope, like we've lost all the A, and now we have dirty B in the pot, and we've got a large flask, so there's still lots of B in there, we'll see the condensation temperature start to creep up. You know, it'll finish the azeotrope, and then it'll start to rise, and it'll go up to the boiling point of B. And so we can boil some of that B off after we've done the fractional distillation. At that point, we're just distilling B, and that pot's getting more and more dirty, concentration of contaminants. But you never want to boil it dry, right? You boil it down to where the still bottom is, a small handful in the bottom of the flask. I don't know how to quantify it, because how do you quantify that bottom part of a round bottom flask? Man, it is really tricky. So I don't like to go smaller than 3 inches in the bottom of a round bottom flask, because I guess it depends on the size of the flask. I use 1 liter flasks typically. So we're getting down to 3 inches. We don't have very much volume at all. So a lot of the solvents that we have are ethers, and those are the ones that are really dangerous to boil dry, because they will spontaneously burst into flame or explode. They make peroxides. And so I don't know how it works, but there must be some sort of oxidation reaction where oxygen comes in and then produces an organic peroxide, and those are shock sensitive and heat sensitive. The organic chemists on the 3rd floor at Oregon State would put this silver bowl in the window and pour they would do an extraction, and they would get their product and they would pour their ether in that bowl and let it evaporate out the window. It's heavier than air, so it would go right down the side of the building and in my window on the 1st floor. You know, I'm sitting here writing my thesis, and I'm like, come on, guys, this ether smell is killing me, you know. And so I thought it was coming out of the drain, like somebody was glubbing the organic solvents down the drain. And so I would fill the P-traps on the floor drains and the sinks and everything around to make sure it wasn't coming up through the drains, and that didn't fix it. And so then I thought, well, maybe there's an air pressure thing. So I put a big gallon bag of water over the drain, like to seal it up, and it was still, I could smell it. So I was like, it's got to be coming in the window. So I went upstairs, right to the organic lab right above me, and I walked in the room and I said, what is up with the ether? And this guy puts his hand behind his back and he goes, why do you ask? And I said, why are you acting so suspicious? And then he said, because we just had a fire. And I said, really? What are you talking about? And he said, well, and he showed his lab coat, and it was like a little charred right here. He said, well, we put our ether in this silver bowl in the window. I was like, first of all, don't do that. It's going right down and getting in my nose. And they said, and just a few minutes ago, he poured the residue in there and it burst into flame and caught his lab coat on fire. And he patted it out and it went out. But then you walked in. So they thought I was spying on him or something. This crazy story, I know, and took valuable 2 minutes from your time. But the ether is a really dangerous thing. And that's all I have to say. Yeah. Okay. What's next?
Are they going to be super complicated graphs, or is it going to be just stuff like the homework?
Just like the homework, I mean, or any of the ones in any of the PowerPoints. Yeah. And we can quickly scroll through those if you want. What I'll do here is let's do this slide sorter view. So this was lecture 17. This compression factor, I won't go into much on that. I just was really showing you that figure so that we could look at this piece right here with where the reduced variables the unitless temperature, pressure, and volume, put all the different gases on the same line. I just thought that was so impressive. And so that's why I showed those. But those aren't phase diagrams, and so we're okay with not doing that. Let's go to 18. Okay, here's the 3D phase diagram. We didn't talk much about the contact angle or surfactants or anything really. It's just sort of a branch off of some of this content. Okay, let's see. 19. Here we really get into the more complicated, the PX and the TX phase diagrams. These are all PX phase diagrams. Raoult's law and Henry's law is in here. You know, in the notes or in the homework, I didn't have this one drawn for you, but here I've got the lines drawn, you know, so these are the Henry's law lines for carbon disulfide. And I was really asking you about this, you know, to estimate when it deviates. You know, here I've got the Raoult's law line, and so I would pick that spot right there. When the blue line leaves the dashed line, then you come down here, you know, and it's like 0.98. Well, did that turn out to be right? Yeah. I thought so. That's what I would estimate. It's like only 2% away. This one, actually, the line didn't get drawn very accurately. You see it kind of comes under the blue line. But yeah, it's, you know, it follows Henry's law. Carbon disulfide follows it for quite a bit longer, you know, maybe between 7 to 10% almost. Look at these. Notice how the Henry's law constants are less than the vapor pressure. So here's K for chloroform and here's P for chloroform. And it's just because these molecules are attracted to each other. So this is a situation where, look at the total vapor pressure. It's less than the pure vapor pressure of either one of the pure components. So it's like it's a way to reduce the vapor pressure of acetone and chloroform. That has a huge impact in storage, right? Because things evaporate. And if you mix these together, you can hold on to them longer. So that's kind of cool. Good question. And no, these are just pressure curves. So these are the partial pressure curves and the total pressure curve. The yeah, that has an upper consolid temperature.
So if it was the other way, it would be
a lower consolid temperature. Yeah, and so that would be in. Yeah, so this, let's look at this, because the PX, this is, what is, let's see, do I have it here? No, I don't have it here. Okay, so if I put it in a container and I pressurize it up to this point right here, what is the phase? Think about it and say it out loud in count of 3, all right? So solid, liquid, or gas, right? Those are our 3 choices. We're right here in a PX phase diagram, and I'm going to say 1, 2, 3, and you tell me what phase it is. 1, 2, 3. Oh, y'all whispered so that you could, so I couldn't hear it. I'm hard of hearing, so say it again. 1, 2, 3. I heard some liquid, some gas. It's liquid. Okay, because you're high pressure. So high pressure. Okay, this is for a fixed temperature. So if we pressurize it and pull the temperature out, and that's the case for a pressure PX phase diagram. Okay, this curve right here is the total PVAP curve. Okay, both of those top curves. That's the pressure, the vapor pressure of the mixtures. So I would have to lower the pressure, and when I get to that PVAP curve, then the liquid starts to boil. Okay. So if I'm right here, if I drop it down to this point right here, then I start to get a vapor pressure. I start to get a vapor phase. So below this point, these are all vapor pressures above a liquid phase. So, yeah. So there, it's the opposite of what you expect for temperature curves, right? So that's. I'm going to point a little arrow at that point. Vapor phase begins. And what would I have to do to go below that point? How am I going to lower the pressure? If the vapor phase has just begun and I keep trying to lower the pressure, all I'm going to be doing is I'm going to be stuck at that pressure until all of the liquid is gone. Yeah. And then when all the liquid is gone, all these curves disappear, right? I just have a gas. And so you can't say what happens when I get below that. I'll just have a gas and all these curves are gone. These are all vapor pressure curves. These are the partial pressures: partial pressure carbon disulfide, partial pressure of acetone, total pressure of the mixture. And so I sit right there at that vapor pressure point, and it will not go below that point as long as I have liquid in the container. This is what we use in vacuum cycle cavitation. So we have our cleaning solution, we pull a vacuum on it, and the water boils, and cavities form in the liquid and push the soil off the surface and out of holes and everything like that. And I can keep pulling that volume and trying to lower the pressure, but it stays at the same boiling pressure, the vapor pressure of that liquid, and it just creates bigger and bigger cavities. Okay. Let's look at the next one. Let's see. Let me make sure there aren't any more in this. The Margulies equation, those are it's just enrichment, telling you how you connect the two ends. You got the Henry's law end and the Raoult's law end, and how can you connect the two, right? And it's this Margulies equation. Okay, so that was 19. Let's go to 20. Okay, then we get into the TX phase diagrams, and you can see here I have it the pressure one on your left and the temperature one on your right. You see how vapor phase and liquid phases are swapped now. We spent a lot more time with TX phase diagrams. I prefer them because they make more sense to me when I look at it and I think of boiling points, because we're pretty much at 1 atmosphere. So we're sort of fixed at 1 atmosphere pressure, like the one on your right, and then we look at all the temperature changes that we have. So temperature TX phase diagrams make sense. Notice I'm saying PX and TX. What's the X in both of those? Yeah, mole fraction. So that's why it's PX and TX. Yeah. Then we got into azeotropes. So here's the high boiler and a low boiler. I'm not making a promise, but typically if I have one on the homework, the other one's probably on the test. That's just the way life works, right? Professors are looking for something to change, but not come out of left field. What are you going to do, right? So just basically make sure you know both, how to work with both. So in this high boiling azeotrope, Michaela, to kind of go on what you were asking about before, what goes in the pot? Like if I'm fractionally distilling this little solution here at A, what's collected in the collection flask? Well, in this case, go downhill. So it boils right here, and then the fractional column does this with the zigzags. And so this is the collection or condensate. And then as we take out that excess A, see this is the mole fraction of A. So over on this side, it's all A. And over on this side, it's all capital B. So as I take out that extra A, then the pot moves left. And that's essentially moving uphill. So the pot will move this way, and we would see its boiling point climb. And then this is going to be the pot. So the pot is always the highest thing on whichever side you're at. Pot composition plus non-volatile residue. We call that NVR. Huge thing in industry is how much non-volatile residue you have in a bottle of solvent. Because if you clean with it, guess where it's going to show up? On your parts. So they wanted less than 300 parts per million. So that's a small, or sometimes 100 parts per million. That's a very hard thing to match or to reach, especially when you have a solvent that might react with light. And so they stick in some kind of BHT, butyl hydroxytoluene, or something like that, with butyl groups and hydroxy groups and all of that, and then that stays behind. And so sometimes it's the additives that protect the solvent that end up on your parts. Y'all are going to be really good at cleaning parts. There's jobs out there, by the way. So then over here, like on the homework, the condensate was here and the pot moved uphill. But if you're on this side, the condensate is still the azeotrope, but the pot moves uphill this way. Over here, if I'm on this side, the condensate is here and the pot moves uphill. So the azeotrope in a high boiler always shows up as the pot composition. Over here, the azeotrope is the thing that's collected. Okay. There's really just two. Well, these double ones and so on. I mean, if I showed you one of these, like this is I would make it a little bit more obvious, like this case here. Like if I were to draw a double azeotrope, see how close those lines are? That's probably realistic, but I would make it more obvious. I would draw it like this. I would make my curve like this. Okay, and then I'd make a pinch point there, pinch point there. Oh, what happened to my other curve? Right, so you can see there's two pinch points. It's hard to draw, but yeah, it's just the azeotrope kind of takes the standard phase diagram and splits it in half, right? So you've got like a simple phase diagram on the left and the right, or in this case, the left and right. And this one just breaks it into three. So like if I was right here, the pot would go this way, pot, and condensate would go this way. So this azeotrope is going to be collected as the condensate. Anything beyond this, anything in these two regions, okay? If I was already very concentrated in this substance, then I could pull some of that substance out as a condensate, but the pot would go towards the high point. Yeah. If I was way over here and very concentrated in this substance, then that pot would go up to that point. But in the middle, the pot would be this azeotrope, and the condensate would be that azeotrope. And then this says partially miscible, right? So this is that two-phase region is just showing you the two dots right there. And so they just didn't draw the upper consolate solution temperature. Yeah. Okay, let me look at the others. This is 20, let's look at 21. This is just the lever rule. I went a little fast on that day because we had, what did we have? We had something that
We finished the game.
Oh, that's right. We finished Azeotropes and then we jumped into this. And so it was, but I think we covered everything. So go through the video on this if you need to, just to make sure you're comfortable with the lever rule. And then that's 21, so 22. Then we get into the solid phase. Oops. Okay, so let me shrink this down. That's where the little bunny rabbit is. Okay, and then we did kind of go fast here at these last ones, these last two. So let's do one of those. Let's look at this. Let's look at the sodium potassium one real quick. Let me just drop you into this phase diagram and let you tell me what phases we have. So again, we've got solids. So anything below this line right here, this is the dividing line between the liquid and the solid. Above this line, we have a liquid phase and a solid phase, okay? So you see this is all liquid right here. And everything below that line is two phases. Let that sink in. Everything below that line is two solid phases, I should say. Two solid phases. Okay. So if I drop you in right here, oh, well, I said that. Let me say everything below that line is two phases. One could be liquid. Okay. So I've dropped you in right here. We're at this temperature and we're at that composition. So what are the phases that are in equilibrium? It's a lever rule. Every one of these is a lever rule problem. So there's my fulcrum, and I draw the line horizontally until I hit something. And so this is liquid, and this is solid. And the solid here is that compound Na2K. And this is the liquid of, I'll just draw it here. It's Na in the liquid phase plus K in the liquid phase. And the composition is right there. It's, like whatever, 60-40 or something. 60% potassium, 40% sodium in the liquid phase. So they're just atoms cruising around as liquid atoms. And then in the side or on the bottom or whatever is a little crystal or amorphous solid of Na2K compound. If I cool it down and I end up in this spot, what are my two phases? Well, that's my fulcrum. Okay. I draw it over here. I have a solid there, and I come over here, and this is still a solid. It just happens to be a dirty phase. So this is a solid phase of mostly potassium with a little bit of sodium in it. So I call that dirty potassium. Dirty K. And then this is pure Na2K, pure NaC. It's okay? Yeah. What if I drop you into one of these little spots? I've got two phases here. One is pure sodium and a separate phase of dirty sodium. A little strange, but that's what I've got. So those little wastes are just a really precise phase diagram. A lot of times you don't have those drawn. Okay. Let's do this next one. And this one does show some incongruent melting. So if I take the just CASI, so 50-50, right? CASI, this is the melting point of that pure substance. And this is the melting point of that pure substance. Ca2Si. But look at this one. This one's a weird one. It comes up here. On your notes, I don't know if you have that line marked out. They had a line that's drawn vertically, but it's actually shouldn't be there. That line should stop right there. And when it hits that 1040 area, that's sort of like a decomposition temperature. So call it incongruent melting, and I'll say decomp temp. Because think about what's going to happen at that point. From this range to this range, in this whole range, it takes that long for the solid to melt. So it starts to melt here. We get a liquid phase, but we still have a solid phase. And if we keep raising the temperature, we still have a liquid phase, and still have a solid phase. The liquid phase is growing because we're getting closer to the liquid phase line. At this point, no solid remains and it's all liquid. So you see, this is a whole temperature range, decomp temperature range. And that's not a pure, that's not a behavior of a pure substance, but it was a pure substance. It was pure calcium Si2, however you name that, okay? And so calcium disilicide, I guess. And so that is a pure substance at a low temperature. But you get up there and it has this melting range as if it's an impure substance. Whereas all the other pure substances, pure silicon, has a sharp melting point. And, calcium silicide has a sharp melting point, and dicalcium silicide has a sharp melting point. So all these other pure substances have sharp melting points, but CaSi2 does not. It doesn't mean it's not a pure substance. An organic chemist would say it's impure, right? Because they look at a melting point sort of to test purity, and this thing melts over a range of temperatures, and you say, oh, I just can't get this substance pure. Well, no, the point is it has an incongruent melting point. Incongruent is just a fancy word for weird. Right? So you can just say that. There's some mathematical definitions of congruent and so on, but I think this is more just strange. Okay, so if I drop you anywhere into this curve, let's say we're right here at 20% silicon, and we'll say close to 910 C. Again, that's our lever rule. We draw the horizontal lines. We've got a solid phase of Ca2Si, solid, and a liquid phase of calcium and silicon ion atoms floating around. If we cool that down, when we get to this point, we will sit there until everything turns to solid. That's the eutectic freezing point. And when everything does turn to solid, we have solid Ca2Si and solid calcium. Which phase do we have more of in those solids? So if I look under a microscope and I see the little grains, which phase do I have more of? Ca2Si, because that little fulcrum's closer to that end. Okay, 5 minutes. Let's keep going. Okay, did that make you feel better about the solid ones, solid phase diagrams? Okay, and that was 22. 23. This was exam review. Okay, so we've covered everything. Huh?
We have water on the poem, like the water phase diagram, and we just have to know because it has the negative slope.
Yes. Mm-hmm.
Would we be given another phase diagram with like a positive slope? I have to know that.
Yes, so that's a PT phase diagram with that slope, like right here. If you look at this one.
Or would we have to like identify it?
Well, if it's a positive slope, you can't know because almost every other known substance is positive, yeah. But you could say that's not water. Like this one is not water because that solid liquid line is a positive slope. So rise over run is a positive value right here. Water leans back.
Mm-hmm.
Yeah. Feel better?
On the homework, we have to calculate the mole fraction. If we have to do that, would you give us the densities that we need?
Yeah, because you shouldn't have to know your densities. Yeah, I don't know my densities. I have to look those up. Yeah. So like if I say that, what layer's on top or what layer's on bottom, I give you the densities. Yeah. Now, if you're given the molar volume of something, it's the volume per mole, and the grams per mole from the periodic table. So don't feel like I'm leaving you out. You're like, I know he's given me enough information. And if you just really are stuck, raise your hand and say, I'm stuck here. Can you help me? And sometimes I say I can't, but sometimes I'll say, yeah, or sometimes people are stuck on the problem because there's a constant or a value on the periodic table that they didn't notice. And I'll say that what you need is on the periodic table, So don't just sit there and just bang your head against a brick, So, all right. Let's do well on this one, okay? Yes.